everyone, my name is Klimovic, and I'm happy to present tf.data, a machine learning data processing framework. This is joint work with Derek Murray, Jiri, Simsa, Ihor, Indyk, and we'd like to acknowledge the whole tf.data team at Google. Data is key to training machine learning models. But before we can feed raw data to a model like a neural network, we need to pre-process the data in several ways. Now, some of this pre-processing can be done offline, and this is things like cleaning or validating the data. We can use batch processing frameworks like Spark, Apache Beam, and Flume in order to do this kind of offline data processing. However, a lot of data processing actually happens online while a model is training. And we call this the last mile ETL pipeline for machine learning. This pipeline consists of extracting or reading data from storage, since a lot of data sets actually exceed the size of main memory. And so online during training, we need to be able to read the data from storage. The next step is to apply transformations to the data on the fly. An example of this is to randomly augment data. So empirically, machine learning models train to a higher accuracy and generalize better if we iterate multiple times over the data set and each time feed a different random permutation of the data. So for example, if you have an image, you might randomly crop, rotate, or discolor the image and feed this different permutation for each training iteration. Now, of course, you could do these transformations offline, but storing all these different random permutations might not be cost effective. Other examples of online transformations include filtering the data, randomly sampling data, shuffling, and batching. In general, the types of transformations that ML users tend to apply online during training are transformations that either add randomness or have some kind of aspect that we want to tune during runtime. So for example, the batch size is a common hyperparameter. Finally, after extracting and transforming the data, the next step is to load batches of data to accelerators like GPUs or TPUs for training. So why should we care about this last mile ETL pipeline for machine learning? Well, a key reason is that it greatly impacts the end-to-end training time and accelerator utilization, which is a key component to the ultimate cost of training machine learning jobs. While machine learning training typically runs on a GPU or TPU, the input pipeline executes most commonly on a general purpose processor. This is because the types of data transformations vary greatly across ML domains and are typically most suitable to run on CPUs. Now, while accelerator performance keeps increasing in terms of its compute capabilities over the generations, CPU performance is stagnating. And as a result, the input data pipeline is increasingly a bottleneck for end-to-end machine learning training. In other words, it's becoming increasingly challenging to feed these data-hungry ML accelerators with data at sufficient throughput. Another reason to care about the input data pipeline is that it actually consumes significant compute resources. We analyzed millions of training jobs in the Google fleet and found that on average, if we looked at the compute time of a machine learning training job, 30% of compute time was spent doing input data processing. So this is why we built tf.data, which is a last mile ETL framework for machine learning. The tf.data API consists of a library of operators that can be combined into a graph by users. This programming model is reminiscent of Dryad Link, Spark, and Naiad programming models. So the tf.data API consists of stateless data sets that users can combine together. And each of these stateless data sets is associated with a stateful iterator that is used to actually produce elements from the data set. Ultimately, this input data pipeline, which is represented as a graph, is submitted to the tf.data runtime, which is in charge of executing it efficiently. And this includes applying optimizations like software pipelining and parallelism, as well as static graph optimizations like fusing operators or vectorizing them, and then dynamically tuning things like the degree of parallelism for some operations and prefetch buffer sizes. The best way to get a sense of tf.data is through an example. So let's take a look at a simple pipeline in tf.data. The first thing we do here is we have an operator to read data from storage. We're using the tf record dataset here. The next step is to apply some kind of user-defined pre-processing. So preprocess here is a user-defined function that is a parameter to the map operator in tf.data. After this, we batch data so that we can submit it more efficiently to the model for training. And in order to actually overlap data preprocessing and reading from storage with the loading of data to an accelerator, we add this prefetch operation to do the software pipelining. And finally, we submit the data set to the model for training. Now, I mentioned that tf.data applies several optimizations in the runtime. So one example here would be to fuse the map and batch operators as part of a static optimization. The dynamic optimization would be to allow tf.data to tune the degree of parallelism for reading data and preprocessing it, as well as the buffer size for the software pipelining. So how much do these input data pipeline optimizations really matter for end-to-end training performance? We looked at 5 different models from the MLPerf benchmark suite, including ResNet for image classification, SSD and mask RCNN for object detection, and GNMT and Transformer for NLP tasks. What we're showing here is the speed up in end-to-end training time relative to a very naive baseline where the input data pipeline does not apply any parallelism or software pipelining. What you see in the blue bars here is the speed up we get in end-to-end training time when we apply parallelism and software pipelining. Here, expert tune parallelism refers to an engineer familiar with the pipeline and the model, delicately tuning the degree of parallelism and prefetch buffer sizes. This could be, for example, from an MLPerf submission. The orange bars here show additional throughput benefits we get when we apply static optimizations in tf.data. Most of these benefits here are coming from fusing map and batch operations in these pipelines. We see that the image pipelines benefit most because they tend to be most bottlenecked by input data processing, whereas for the text pipelines, just applying some parallelism is sufficient to reach the point where input data processing is no longer the bottleneck for ML training. And the green bars here show that when we enable tf.data auto-tuning, we get very similar performance, which means that even novice users can benefit from properly tuned parallelism and software pipelining in their input data processing steps. Now, having built tf.data and deployed it across jobs in the Google fleet, we were curious, what can we learn from the millions of machine learning training jobs and input pipelines that we have running? Our paper has more details about this study, but I'll highlight 2 key results in this talk. One of the things we were curious about is, how does the volume of data vary as we're doing data processing? We mentioned that some transformations, like random data augmentations, expand the volume of data, whereas others, like filtering or sampling, decrease the volume of data. So how do these things balance out in the end? What you're seeing here is a CDF, and on the x-axis, we have the bytes produced by an input data pipeline and fed to a model, divided by the bytes read from storage. And so if this ratio is greater than 1, then we increase the volume of data. And if it's less than 1, we're decreasing the volume of data. Now, if we look at the blue curve here, which is for end-to-end pipelines, we see that on average, out of the millions of jobs that we studied, 75% of jobs tend to do pre-processing that ultimately decreases the volume of data. So this suggests that maybe we don't want to be doing pre-processing all locally on a training node, but instead push some of this data processing closer to storage. Another question we were curious about is, how frequently are input data pipelines re-executed? We had a hunch that this might be high because a lot of common training workflows like hyperparameter tuning or model search involve tweaking the model while keeping the input data pipeline the same. And indeed, what we see here is a CDF with, on the x-axis, the number of input data pipelines that are unique, ordered from most to least frequently executed. And the dotted blue line here is a CDF of the input pipeline executions. The orange curve also shows input pipeline executions, but each pipeline is weighted by its compute time. And so these large jumps in the orange line show input pipelines that tend to be particularly expensive to compute. And what's remarkable here is that in our study, 10% of input pipelines accounted for 77% of input pipeline executions and over 70% of the total compute time spent in tf.data. So there's a few heavy hitters that would be very good to identify automatically and reuse the computation from their input data pipeline as opposed to re-executing it each time. Thank you very much, and I'm happy to take questions. Please feel free to reach out.